Hi, my name is Kara Lindstrom. I am a rising junior studying mechanical engineering with a minor in computer science. On our RoboSub team, I am the head of the mechanical subteam, and I will be talking about the configuration of the thrusters.
Hi, my name is Muthu Aravoli. I'm a rising senior here at Duke studying electrical and computer engineering. I'm the electronics team lead here at the Duke Robotics Club, and because of this, I worked on designing the electronics behind our propulsion control system.
Hi, I'm Nick Chakraborty. I'm a rising junior here at Duke studying computer engineering and physics. I'm co-president of our robotics team, and I helped develop our propulsion controls algorithm and software. Our propulsion system has three main aspects: the mechanical design and placement of the thrusters, the Arduino microcontroller, and the controls algorithm, which allocates power to the thrusters to get from point A to point B. We will explain each part of the propulsion system in detail. First up, the mechanical design.
The basis of our design was a wide, flat frame with 8 thrusters mounted to it. 4 vertical thrusters on 2 opposite sides of the robot, attached to the legs of the robot, and a horizontal thruster on each corner. Additionally, we went for a multi-capsule design to better distribute weight and even out the load each thruster would have to propel. So we have our main electronics capsule, we have our pneumatics capsule, and under here we have our battery capsule.
Next up, the Arduino system design.
In order to connect the physical thrusters with our higher level controls code, and to actually power the thrusters, we use an Arduino connected to a multiplexer connected to our multiple ESCs. We use the ROS serial package, which allows us to write C-like ROS code on the Arduino itself to input data from our control system, which uses ROS for communication. Since the Arduino Nano doesn't have enough pins to control all the thrusters, we use a PWM multiplexer, which is connected over I2C, to actually distribute the PWM signals used to control the ESCs. The ESCs are then connected to the thrusters, which are outside the capsule using CCON pizza connectors.
Lastly, our controls software design. Our controls algorithm is based on PID, proportional integrative derivative loops. When our task planning code tells us we need to go to a certain point, our PID loops allocate power to the thrusters by calculating whether we are on course to reach that point using our sensor data. If we are off course, our PID loops automatically tell the Arduino to adjust. In this way, our robot control is reliable and fully autonomous. Movement in 6 degrees of freedom is required for the AUV at competition. The entire purpose of our propulsion system is to allow our task planning software team to direct the robot to any desired position or maintain a desired velocity without having to worry about the nitty-gritty implementation details. We will first discuss the rationales for design across each propulsion subteam. Let's start with the mechanical design.
For our choice in thruster, we went for the standard blue robotics T200 thruster because they are very cost effective and we have past experience in using them. For their placement, we put them on the edges of a wide square frame in order to maximize the amount of torque that could be applied for barrel rolls and rotation in all directions. Not only will this help us achieve basic movement and style tasks, but it would also assist in facilitating the position of actuators such as the claw, which is not yet in this model, and the torpedo launchers, which you can see here.
Next up, the rationale for our Arduino system design.
We use an Arduino to abstract the physical design of the computer we use away from the robot. The main advantage of that being we can use any computer. This allows us to easily switch computers back to our old NUC should the need ever arise. We use an Arduino Nano over the larger Arduino Mega due to physical space constraints in the capsule and to avoid unnecessarily long and complex wirings. With regards to the power distribution to the thrusters, we use the fused but unregulated battery voltage, meaning that the overall power output and the efficiency of the thrusters varies with voltage. This causes no problems, however, since our higher level controls algorithm provides us with relative thruster power and not absolute thruster power. Due to this, we save space in the capsule by not using large high-powered DC-DC converters for the thrusters.
Finally, the rationale for our controls software system design. As detailed before, our controls algorithm uses PID, proportional integral derivative loops. These loops are the industry standard, and they're by far the best option because they provide the most flexibility. PID is a feedback loop. It continuously minimizes an error value that measures the difference between a desired set point and where the robot currently is. This feedback process is going to work no matter where we place the thrusters, hence the flexibility of PID. We can adapt the same process to velocity control as well, and that can be useful for tasks like the barrel roll, which just require yaw velocity. We improved our existing PID this year by introducing nested position velocity PID loops. This makes our control system very resilient. Currents and disturbances in the water, which were problems before, no longer throw us off course, as the inner velocity loop, which runs at a very high frequency, will immediately correct the thrusters. We will now discuss our specific competition strategy for propulsion control, assigning confidence ratings to each task. The gate task is required, and our robot propulsion is very equipped to steer us through, from a mechanical, Arduino, and control standpoint. Our confidence rating is 5 out of 5, and we can also get some barrel roll style points. We're similarly confident about the buoy task. It should be no problem to bump the buoys with our control system, so 5 out of 5 confidence score there. The bins task is slightly more difficult. We're concerned about drift in our controls algorithm when positioning our robot over the bin. Regardless, we still have a confidence score of 4 out of 5. With some PID tuning on site, we should be fine. Similar story for the torpedo task. We give it a confidence score of 4 out of 5, since we'll still need to do some PID tuning on site to make sure everything works. We're confident in our ability to follow the task markers so that our robot will not get lost. Task markers are things like the lines and the pingers. The only very difficult task for us is the octagon task. The propulsion is hard. It'll need to be very accurate to guide the claw toward the bottles. There are other difficult factors outside of propulsion as well, like refining the claw mechanism itself and planning the task in software. It's too complex for this year. Our confidence score for the octagon is 1 out of 5. We would not attempt it in in-person competition. Given the online nature of the school year, most of the propulsion testing was done in a custom virtual environment that we put together. The virtual environment simulates a multitude of physical factors, such as buoyancy and water currents. We created a URDF model of our new frame design, and we formulated models of the various tasks, like the gate, for example. The visual part runs in a program called CapiliaSim, but all of the background math runs in Python, making our simulation very flexible. We first tested the mechanical frame and thruster placements in simulation, and we found that the robot achieved 6 degrees of freedom without much trouble. Then we tested the controls algorithm in simulation. Our main victory was validating the new nested PID loop's ability to move the robot to a desired position or a velocity set point. Our robot rarely overshot the mark when it came to attaining a given set point. The PID loops demonstrate resilience to currents and disturbances in simulation, which is a huge plus because those things happen in competition all the time, little currents and disturbances in the water. We were even able to tune the PID constants in simulation using a Ziegler-Nichols auto-tuning script. We simulated barrel rolls and rotations, and the robot performed well all around. Later on in the year, we were able to actually get in some in-person pool tests. Most of our testing results from simulation carried over to the actual pool, which is fantastic because that means that our virtual simulation is close to reality. The robot again demonstrated resilience to currents and disturbances while moving toward a set point. Even the robot PID constants carried over to simulation. We barely had to tune in person. Testing in person was important for validating our Arduino system's ability to tie everything together, because that's one thing we could definitely not test virtually. And it turns out everything works. All thrusters activated when the Arduino sent the signal, meaning the multiplexer system was working, and the power supply for the thrusters was sufficient. One concern we did have early on was that we had a few resistors in the circuit that overheated. However, we were able to resolve that by reorganizing and resoldering the circuit. The biggest propulsion challenge in past years for us have been depth holds, getting the robot to stay at a specific depth. However, our recent in-person pool tests have shown that our robot can actually perform the depth hold very well, even while performing a barrel roll. We credit our nested PID loop system for this new ability. We were able to do some additional mechanical testing in the large sink in our lab. There, we again verified that our robot frame and thruster placement could achieve 6 degrees of freedom. We also found that we were able to use significantly less power compared to last year for a roll, since our thrusters were more widely spaced apart, so that increased their torque. One thing we did realize in the sink was that 8 of the thrusters would have to be protected so they didn't get banged up during our rotations. We designed thruster guards, and when designing these thruster guards, we hit the guards with mallets to test them. We compared breakage locations to finite element analysis in CAD. And in that way, we were able to very quickly iterate the design until we had good thruster guards. Overall, despite COVID-19 restrictions, we were able to test all aspects of propulsion control quite thoroughly, both in a virtual simulation and in person. Our mechanical, Arduino, and control systems all work as they should. With this strong base, we're in a good place to truly develop our task planning algorithm to the highest level for next year's competition. In the future, we plan to do more in-person pool tests. This should get easier now with many COVID restrictions being lifted. The main purpose of these pool tests, propulsion-wise, will mainly be PID constant tuning. We want to make sure our controls algorithm is as precise as possible for next year.